Hello and welcome everyone to MSc Software's webinar series. Today's topic is Marc 2018 Increased Solver Accuracy and Improved Rubber Simulation Workflows. My name is Farnaz Jadbabi and I'm the Product Marketing Manager for Marc and MSc Nastran. With us, we have Matt Kokali from the Product Management team for Marc, and we would like to show you some of the new enhancements that have been added to the exciting release of Marc 2018. The first section, I'll be talking about some of the improvements that we have added to the Marc 2018 release. These improvements include enhancements to seal and rubber workflows. In addition to that, I'll be talking about improvements that have been added to contact analysis, especially in terms of accuracy and efficiency. Next, we'll be talking about the material data fitting capabilities in Mentat. Addition to that will be the interoperability and the ability of Marc to work with other FEA solvers. The next section will be covered by Matt, and he'll be talking about the usability features that have been added to Marc to improve your simulation workflows. Some of these include improved fastener modeling with bolts and springs. Next, he'll talk about the multiphysics capabilities that have been added to the 2018 release to improve the efficiency of induction heating simulations. And he will also talk about the convergence control options that have been added. The localized checks will provide more accurate models. Later, we will talk about some of the additional news for Marc 2018, especially for those of you who are interested in rubber fatigue analysis. So we can go ahead and start, but before that, I want to let you know that we have made some changes to the default color map in Mentat. So if you start your processes and you see that the color mapping is different, please note that this is there by design and it's not a bug. This is done to improve the visibility of different objects when you're using the color mapping system. So in this section, I'll be talking about the improvements that have been added to seal and rubber modeling workflows. Recent industry demands are a leading force for most of engineers to deliver higher quality products with a faster turnaround time. Marc 2018 can remarkably help you overcome some of the issues and industry challenges that you're facing by enabling an early assessment of hyperelastic materials to improve the simulation workflow for design of these rubber types. As far as the modeling application, these rubber materials and the viscoelastic types of materials are mainly used as shock absorbers or dampers to minimize the vibrational effects in vehicles. During cyclic loading of these viscoelastic bodies, we see the mechanical energy that is released in form of heat, and later on the resulting heat creates some temperature changes and temperature increase in the material properties. And the temperature increase results into an irreversible degradation in the physical properties of the materials. And you all know that the long-term material degradation of material properties can significantly impact the operational performance of structures and create some later on create some issues. So to address these type of problems and challenges, Marc 2018 provides a coupled sequential simulation workflow that allows you to easily calculate the self-generating heat from vibrational loading of these viscoelastic rubbers. It's a very simple process, and that starts through a harmonic load case to calculate the associated viscous energy dissipation at a single frequency. Just want to let you know that there is no temperature dependency at this stage. However, this load case is followed by a steady state or transient thermal analysis load case where the harmonic data are used to derive the heat generation. And this allows you to calculate the temperature evolution of the viscoelastic material components. The coupled sequential analysis makes it much easier for you to perform these modeling simulations and improve the design of the rubber and seal workflows. Results also could be thermal flux or equilibrium temperatures depending on the solution that you're working with. Here you can see a sample model of a damper with two metal ends. Generally, we have a lot of models. However, they're not easy to show you because some of them contain proprietary materials. So unfortunately, we have to show you the simple ones. You can see in the left image the damper model. In the middle one, we have the harmonic stresses that were calculated in the harmonic load case. And then followed by a thermal load case where you can see the temperature distributions. The second enhancements that have been added to the rubber workflows is the ability to capture and duplicate the strain softening of viscoelastic materials. Studies have shown that these materials exhibit degradation in their mechanical properties when they're subjected to cyclic and repetitive loads. This phenomenon is often referred to as the Moulin's effect and is one of the most important options that you need to capture, and it's most prominent during the first couple of loading cycles. Again, as I said, it's important that you take into account this effect as it can significantly impact the in-surface performance of the structures. To overcome these challenges, Marc 2018 provides an additional damage model called the Ogden-Roxburgh model to accurately and efficiently capture these complex behavior of materials under cyclic loading. We want to make sure that you have this option in case you want to use it. The decision on which damage model to use is dependent on what type of analysis you're doing, what the user believes in, and what your constitution or company requires. So there are several damage models available, and the new OR model has been added to increase this capability and expand the modeling simulation modeling of rubbers. The damage state variable can be written to the post file, and we have also added the material fit capability in Mentat to cover this damage model, which will be covered in the next slides. Here you can see a use case of this enhancement in a Jounce bumper. To capture the degradation of automobile rubber boots from a regular operation. This model was used. Here on the left-hand side, you can see the axisymmetric model. And in the middle, we see the loading sequence. And we also see the deformations at maximum load case. You can view the stresses at highest loads. And on the lower side, in the middle, you see the damage model, the damage that was accumulated during the loading. And finally, on the right-hand corner, you see the load displacement curve for the total model. So this is for the total Jounce bumper. Next section that I'll be talking about is related to the contact enhancements that have been added to Marc 2018. Contact modeling of large assemblies that consist of hundreds or thousands of components is often a very complicated task that requires a lot of time and in-depth understanding of the load path and the contact body interactions. So we want to make this process simpler for you and make your modeling as efficient as possible. So in order to do so, in Marc 2018, we have provided a new automatic contact detection method that enables you to easily generate or modify contact tables based on the physical proximity of parts. we're trying to make this more efficient and accurate. You all know that Marc has always been good with context, so with the new enhancements, the process gets easier, and also the chances of making mistakes are reduced, because whenever you have to click a lot of times from here and there are chances that you run into some modeling mistakes or potential errors. So replacing this manual process with an automatic detection of the contact definition can significantly help and reduce the chances of making mistakes. Additionally, as a user, you have the option to define whether you want to replace the existing contact definition or add this to the contact table. So first step is that you have to define the contact bodies, and then next you specify the contact type, whether it's touching or glued, and then you define the maximum contact search distance for the detection algorithm. And then the solver will look at the distance, and any two bodies that are within the distance tolerance are defined in contact. And again, as I said, you decide whether you want to replace the existing ones or keep them. This is also beneficial and can be used as a quick modeling check in cases that you have made some contact definitions and you want to compare it, and you can verify it with the automatic method and see whether they work properly or not. Also, the newly generated or modified contact table entries can be edited and with manual entries. So you can stop the automatic method and have the old method that you were using before with the manual entries. You also have the option to exclude self-contact if it's beneficial to your modeling process. In the next slide, we'll see an example of a contact model. Here you can see this is a large assembly that has multiple components. It's a barge part that is mainly used in transportation industry. And in this model, we had a total of 139 bodies. So imagine trying to define contact pairs between these bodies. It's going to be very tedious. So the automatic contact detection was able to create around 275 contact pairs. It makes it, again, as I said, efficient to use and more accurate, as it reduces chances of modeling mistakes. So here, another enhancement that has been added to contact analysis is related to improving the accuracy of contact definition for rigid bodies. This is done using a new faceted representation. This is in particular value for using manufacturing and other simulations that require rigid surfaces for contact. With the new 2018 version, you can easily import the STL triangles as a single faceted surface and assign those triangular faces to a geometric contact body. Similarly, if you have parasolid geometry available in the model, the parasolid faces can be used and converted to the faceted surfaces. This is very beneficial, as if you have hard edges in your model, the hard edges are automatically detected by Marc, and generally using the STL triangles allows the solver to internally use the smoothened surface algorithm that is similar to what is already used for deformable bodies. This results in an improved fidelity in the rigid contact body definition. Now, when you have the parasolid geometry available, you have an additional improvement where it calculates and detects, automatically detects the hard edges, and also because of having the faceted surfaces, you can get a smoothened surface if you have an area that has a curvature. So you get to capture both the curvatures and the hard edges. Also similar to faceted surfaces in 3D, you can now have faceted curves that can be used for 2D models. Next slide, we can see an example. On the top side, we have a simpler model. On the left side, you see the parasolid sheet body, and on the right-hand side, you see that how it is converted into a faceted surface. The lower portion, we have a more complicated model with various curvatures. So in the middle one, you see the smoothened surfaces. Although it's a complicated model, it's capturing all of those properly. And on the right-hand side, you can see the results and the hotspots, how the curvatures have been captured, and we see that results are matching and what we expected to be. Next, I'll be talking about material behavior and enhancements that have been added for data fitting capabilities in Marc. As far as material data fitting, we just made some improvements to efficiency and quality and robustness of the data fitting processes that have been existing in Marc, and also expanded the library to provide additional models. Instead of going through the whole operation of taking experimental data and fitting them manually, we're providing the automated method for your benefit, and this makes it much faster, and you can start making a comparison between material models in a quicker format. The previous Marc releases, material data fitting engine was also available and was supporting many models. However, in this one, we've introduced new ones. Various material models can be successfully derived from experimental data. And here you can see the form that is used in Mentat to do these procedures as an example. Also, it's using the ragged tables. Fully generalized Mooney material is supported. The volumetric strain energy can be fitted using a single box modulus or using a series expansion. So these are all supported. And also, as mentioned previously, the newly added Ogden-Roxburgh damage model is also fully supported by the new material data fitting capabilities of Mentat. In the next slide, we can see some of the curve fits that we have done as an example. So on the top side, you see the independent hyperelastic material data fitting with differential evolution, or you can see in the middle the Ogden data fit without volumetric data. You can see from the curves that the red is the fit and the green is the experimental data. You see that the fit is pretty satisfying and is within the limits of the material definition. So it's a pretty accurate process. Next, I'll be talking about the interoperability of Marc and the ability to work with other FEA solvers. As much as we all want to stay within one platform, sometimes it is required with today's complex models to exchange data between different solvers and share information across multiple platforms. So Marc 2018 provides significant improvements to allow a streamlined interface with MSc Nastran and Abacus. For MSc Nastran side, we can transition the model from a linear run to a nonlinear run in Marc. Please keep in mind that this is a literal translation and it is not going to give you a perfect model. It will just try to look up everything that it reads from Nastran and find the equivalent Marc entry. So it provides you some definitions. And also the reason that you may not be able to completely transform all the materials and all the information that you get from Nastran into Marc is because some of the features that are supported in linear analysis may not be 100% supported with a nonlinear. So it's important that you pay attention to it. The new part is regarding the translation of materials from Abacus models to Marc. This is to add additional flexibility to users, and this is the first release and supports some of the most common Abacus keywords. We're planning to improve and increase it as the future releases come. So again, this is literal translation and does not support Abacus keywords where an existing Marc capability does not exist. And with the you can do that by running it from Mentat or via the command line using the Abacus to Marc input translator. And once you do that, it's a ready model that can be run. And also a log file is generated for your reference to see and follow the procedure and see what happened. The next slide, we can see an example. It's the same contact model that I showed you previously. We chose this because we wanted to show you how the contact definitions that were used in MSc Nastran can be translated into Marc. So some of the Nastran cards, such as BC Para or Beacon PRG or BC Table for contact definition, have been translated. So all the contact bodies, contact tables, touching and glued settings, breaking glue or separating glue. So all of these have been successfully translated from MSc Nastran to Marc. Similarly, you can see from Abacus point of view, some examples are shown here. We have some keywords that translate nodes or element types from Abacus to Marc. Contact is something that we want to implement properly, so we see D2D or R2D contact pairs. These are the Abacus definitions. An important benefit here is that the Abacus to Marc translator generates a ready-to-run Marc model. So this is the main goal of this translation, to get a model that you can easily run. So if you have an Abacus model that you would like to import in Marc for further analysis, 2018 version allows you to do so. At this point, I will hand in the presentation to Matt, and he will start talking about the usability and other enhancements that have been added in 2018. Thank you.
Thank you, Farnaz. Just a quick sound check.
Yes.
You can hear me okay? Okay, great.
Yes, perfect.
Great. So I'm going to talk a little bit about the usability improvements we've done. This is a big activity for us moving forward. We're going to put a lot more effort into the usability. We know that the models are significantly larger, bigger, more complicated than before, and there are things that we can do to make that easier. The one thing that we did do in this release towards that in March 2018 was improve the selection options in Mentat when you have solid geometry present. So a little bit on us to not be leveraging the solid geometry like we should have been all along, so we've rectified that. And the real goal of this is that we want to improve your efficiency, obviously, when you're picking any feature applied to a geometric entity, whether you're going from a solid geometry to a FEA representation or vice versa. So there's a lot of different menus. I'm not going to go through each one of them, but the left side menus, let me just turn on my laser pointer. These left side menus, they talk about how you can select solid vertices via either higher order stuff or lower order stuff, or FEA things like nodes and elements, or color. Just a quick note about color, we'll show that next page. It's very hard to really organize a solid representation. You'd be very interested to see if this is something valuable to the community, if coloring different faces for different things, if this gives you an easy way of other than a tree, of course, of actually organizing your model for selecting different things. We know those are setup costs, but it will be interesting to see, and we can see that in the slide I'll show in a second. And then likewise on the lower right, the four menus there talk about selecting nodes and elements and lower order edges and faces using solid bodies. So we're hopeful that this is going to add a lot of flexibility for you guys, a lot more ease to select. So you can see here's an engine block. Obviously, if you knew you were going to frequently choose or want to select certain faces of that for different operations, you might want to color it differently. It might actually help as well, just for looking at it as well when you're exploring the solid that you're working with. So here's an option where if you had colored the cylindrical bores and you just select them, you could select those by color, and likewise for maybe that top where you're going to have a gasket type material. Another thing we've done in terms of usability specifically to particular functionality has to do with multiple springs and fasteners or bolts with preload. So we have not had a user-friendly way of really assigning fasteners, and we know that assigning springs can be, when you have the same properties across many different springs, can be quite tedious. So we've made some changes to make that much easier. Obviously, if you have an assembly with a large number of fasteners with preload or springs in themselves, this is going to add a lot of value to you. The implementation, the first thing we did do is previously we didn't really support large rotation and displacement for that cross-section option. So we've rectified that issue that you need for the preload of fasteners and bolts. And then we streamlined the process for actually defining that preload. You just select the elements of the bolts, and then Menta will automatically create and position control nodes for those bolts. You can apply then a boundary condition for preload by selecting the control node, and there'll be a set created, or by a special filter, you can do the elements of the bolt if you don't want to select the nodes. The actual direction of the bolt is automatically determined and updated by Marc, as it should. And during post-processing, the bolt force is plotted in the current direction, also as you would expect. There are special global variables for control node displacement, as well as axial and shear force. These are the things that we generally find are of biggest interest to the end users. And multiple bolts can quickly be generated through a single action. So it's very fast, it's very efficient. If you're doing preloaded fasteners or interested in preloaded fasteners, this is definitely something you want to go to the release guide and look at. And as always, feel free to reach out to us. The other part of it was springs. Springs are now handled as elements. And as a result of that, you can apply the same stiffness or damper properties to multiple springs, like you would a material property. And then you can now activate and deactivate springs per load case like you would any element. So we think that this is going to add a lot of value. Here's an example with a satellite dome assembly. There are 168 bolts modeled using beam elements. This was set up in minutes. And then, of course, we made sure that it did preload, and then we loaded up as well. So this is definitely an exciting capability if you're dealing with this kind of assembly. And then finally, some general Mentat usability improvements. So sometimes these are the ones that make the biggest difference because they're little things, but you run into them constantly every day. We're interested in doing more of these. So as always, reach out to to us or to your field as well, your local rep, to tell us what you're interested in. We did the new rendering defaults. So as Farnaz mentioned in the beginning, the default color and contour map schemas have changed to make them more consistent with what's the standard today, and also just make them generally more easily visible. Nodes, points, and vertices are not plotted by default. So, again, the model sizes are so big that you don't want a cloud of points, so we're not going to plot them by default. Elements, solids, and model sections are also plotted as solids, and this is something that we find our users generally prefer. There's visibility of specific model features and definitions we've done. So highlighted and selected nodes, points, and vertices are going to have different symbols in order to better see what you picked. The one I want to make sure you do see is this one up here in the upper right. Non-editable fields are italicized so that it's clear what's, based on, in this case, based on the option. Since you're not doing automatic, you're doing manual, this is the factor that you would adjust, and if you had obviously selected automatic, this would disappear, and this is still non-editable because it's automatic. Filters have been added to easily select post-processing quantities, and we started there, and we hope to extend that further, these filters. And icons now to set the lookout point. So this is a commonly requested thing for many years, this ability to set that lookout point for the center of rotation. And now we have a very simple operation. You just click that icon and then go to the thing you want your center of rotation to be about and select it, and you can change that. There's also some new interface options. Probably the one that's most interesting is even if your nodes are not visible, you can select them. So if you're just, I did that here. I just had the elements visible, not the nodes, but I could still select these 3 nodes. I just used that today, actually. It's very nice. And then some of the user stuff we had that would interrupt things when it shouldn't. We've cleaned up a few of those. Just a discussion real quick about some of the multiphysics stuff we've done. So we've extended support for symmetry and cyclic or anti-symmetry to additional physics and job types. So we've had this already for certain of the physics, but not all of them. And so we're, again, closing the loop with these and making sure we're extending them wherever they make sense. In this case, we were actually very highly driven from a particular application, which is gear teeth hardening via the induction heating. And for that reason, we extend support for plane symmetry and cyclic symmetry or anti-symmetry via contact options as a boundary condition to thermal, electrostatics, magnetostatic, and magnetodynamics. They support coupled and sequential analyses, obviously, as long as those physics are supported by the coupling or the sequential. So, as I said before, we are driven by this desire to better capture this induction heating. As you can see in the old process without these symmetry planes and these anti-symmetry, cyclic symmetry planes, this would take a very big model. And what we can do is, of course, cut it from 18 teeth to just modeling 1 tooth, and then cut that in half as well and model 1/36 of the actual model. So as a result, this model can run in 30 minutes versus a day. We do the same thing we did before, except with the magnetic induction, except now we can do it on a smaller component because of the symmetry. Calculate the temperature over time, and then using our existing capability for phase transformation as well, we can then figure out what phase you have. So this whole thing can be done very quick. You think if it's in 30 minutes, it's actually very fast, and that's the goal of any of analysis is to get it under an hour. Sometimes we'll be successful, sometimes just the laws of computing isn't there yet. But we are very happy to be able to do this use case this quickly. And then I'm going to talk about convergence. So I like to think that we have in every release one enhancement that ends up being a big surprise in its extent of what it touches. I think this is going to be one such enhancement. I'll also say this is some of our continued focus on the core solver. Obviously, we're always working on things like performance and scalability and that sort of stuff. But there's also things that we can do, right? There's the industry itself is somewhat, I think, stagnated when it comes to the core solver, and we aim to change that. So we introduced a new thing in Convergence that we think is going to be very exciting. And before I even get into it, I will encourage you to at least give it a shot if you think it might apply to you. The more input we get, the more we can fine-tune it. So the way this works is you're going to do your normal convergence checks the way you always do your convergence checks. There's just a new option. And what this new option does is when you turn on this equilibrium per node, is it's now going to do a check as well. In addition to the other global check it does, it's going to check for the residuals and the maximums criteria at individual nodes. Really what we're hoping is that you may get some efficiency gains, and we'll talk about that in the example I provided. But we also are excited by the accuracy we've seen for a wide range of simulations we've already done. So implementation is actually really simple. You're just going to click equivalent per node. Probably the only confusing thing has to do with these different levels. So if you select mild, what it really does is a check for the equilibrium condition in individual nodes. And if it is not satisfied at any one of those nodes, it will force an extra iteration, but it's not going to do anything more than that. We found that that actually in itself can be very helpful because we think it's converged on a global level, but locally there are some things that we know later on could cause problems downstream because it's not locally in convergence. And sometimes that addresses it. We also have standard and strong levels. And these basically just change the fraction of unequilibrium nodes allowed. So it'll continue in this case until 0.5% of the unequilibrium nodes are in equilibrium. In this case, you're only allowed 0.1% to be not in equilibrium. Now this can change. You can also manually change this. You can theoretically put 1, in which case the functionality really is very similar to the mild, or you can put 0, in which case it's going to continue until all local nodes are in equilibrium. Just from my brief time with it that I've done, our QA guys and development guys have done more. As product manager, I wish I could use the code even more than I do, but I did. It is problem dependent. So obviously, the more nodes you have, that might impact what percentage you pick. And also, how severity is localized in your model as well. That could impact what your fraction is. So it's going to be a bit of an interesting change for us to figure out what kind of fraction might be the best fit. But we do think for the standard and the strong, those are good defaults to try. You can request postcodes related to that convergence process, the residual force, the moment, the force convergence ratio, and then local force convergence status. So you can get all the data on what's happening locally as well. It'll actually write it out. You'll notice it in the log file as well. You will see how many nodes that weren't satisfied as it goes through. So there's a lot of feedback, which is good. What's really interesting is looking at these use cases. I actually ran 2 of these just as I was investigating some other things around the core. And in both these cases, the green curve is what you get as is, using just the standard convergence criteria. The red represents what happens when you turn on local convergence. So I was able to get red using the old method, but I had to refine the mesh significantly more. So you can already see from an efficiency point of view, just not having to mesh is finer, and able to get some good results is great. I'm not saying this is a cure and you can run coarse meshes everywhere. I'm just saying that this I think speaks to some of the accuracy we're getting from this effect. Getting rid of this erroneous drop and getting rid of this sawtooth pattern is definitely something that we find to be very exciting. We also have a much more complicated models. As Bernard mentioned, sometimes it's hard because we can't really show it. The good news, at least with this one, is we can show things that don't tell you what that model is really at all. We kind of took a close-up of here because this is where sometimes it's a little interesting. We can see, and I apologize for the eye chart, it's really hard to see these little numbers, and there's little jumps and dips in here, similar sawtooth kind of pattern. Before and afterward, there's literally just 2 points or 3 points. There's one right up here that I didn't capture, but basically it smooths it out really well, and the results are consistent, but we just don't have that noise, so to speak. So the local convergence option, I really encourage you if you're running on a model. You do pay a small penalty in the fact that you're doing an additional check. Again, it'll be problem size depending on how big that is. But the thing to keep in mind, the other thing that we're finding is because we are not having situations where we're deviating from what the real response would be, we don't have a situation where you might converge a criteria, increment not accidentally, erroneously. and there's local convergence problems, and then that fails in the next increment. This will help prevent that from happening. So for a wide selection of problems, I really encourage you to check that out. We did have some other performance and documentation improvements. We did improve some of the responsiveness of MenTap for large 3D solid models and have some OpenMP support. But in this slide, I really want to bring to you about the documentation. We've tried to improve the user's guides layout. This is a work in progress, but we are putting effort there. And the other thing we've done is tutorials for crack propagation and advanced thermal analyses. We know that these were a little more difficult to do with the given documentation, so we've introduced some tutorials. So feedback on those, if you do look at them, you do have needs, it would be great, because we want to continue to improve those, and if those are well received, we of course would like to do more of those. Finally, I just wanted to mention as additional news, this is not an MSE necessarily functionality that we have, but we have a new partnership with Endurica that if you're doing rubber fatigue, this ties into the very beginning of the presentation where we talked about seals and rubber type activity. Endurica has a compatible add-on with Marc MenTap, and so if you're interested in what's going on there with rubber fatigue, or if you're already using Endurica and you have Marc, now is the perfect time to reach out to them to see what they can do. And you can always contact us, and we'll be happy to put you in touch with them as well.
At this point, I would like to thank everyone for joining this webinar, and thank you, Matt, for the very informative presentation. Hope to see you all in future events. Have a nice day.